Okay, I just want to welcome everyone to the first seminar of our winter series of Wednesdays at NICO. Thank you guys for coming in person, those of you that are here and not online, because it is terrible weather today, but you made it. And as a reward, we get what I expect to be a great talk from Matt Ives. Matt is on the faculty at INET, the Institute for New Economic Thinking at Oxford, but he's also now local here in Chicago, the Chicago area. He does, as we'll hear about today, I think, a lot of modeling related to climate and coupled climate and human systems. But interestingly, I learned in looking through Matt's profile that he also used to study fishery management, quite I think, an interesting area. In general, the ecology, I guess, is the connection, but and water resources. But I think we need more. I think this is what NICO is for, this crossover between different disciplines and the intersections of disciplines and study of complex systems. So I'm interested in hearing what Matt's going to tell us about today. Just a reminder before I give the mic to him is that NICO will have seminars, I think, every Wednesday for the rest of the quarter. Please take a look at the schedule. There is one special Wednesday up here. The lightning talks on February 7th. I think we still have some slots. So take a look if you have something you can present pretty quickly and you want to volunteer. Please send an email to nico@northwestern.edu. Also, there's the ad, or there's a sign up link also. You can take a quick photo of that. Also, NICO Reading Group. Consider joining that if you're interested in learning more about complex systems and reading papers. There's also our data science nights. Keep an eye out for the upcoming data science nights. Sign up for the NICO mailing list if you're not already on it. And all right, with all that said, well, let's welcome Matt, and I'm looking forward to the talk. Thanks, Matt.
Yeah. Thanks, everyone. Thank you for coming. The reason I moved out of fisheries was because the biggest risk to all the fisheries in Australia, at least, and I'd pretty much say the world over, was climate change. And so when they closed down our research station in sunny Sydney, I decided to go to Oxford and do some research in climate change, modelling human systems this time. And I was fortunate enough to work with a great group at the Complexity Group that's in the Institute for New Economic Thinking. So a bunch of names here. As you know, whenever you're working in a lab, there's a lot of people that are involved in the research, and a lot of what I'm going to show here involves a lot of people, my colleagues, and some students. And what we're doing, what we were involved in was an idea of is there a way to accelerate our decarbonisation of the system? If we had to put in a carbon price 30 years ago and slowly ratcheted it up, that probably would have been a better solution. It would have led to a slow but necessary change and move away from fossil fuels and other emitting sources. So what I'm going to do is talk to you about the fact that we're now in a fairly desperate situation to accelerate that decarbonisation. And so we're going to need something more drastic. And we had a look at the possibility for sensitive intervention points in the system that might accelerate the decarbonisation. So I'll just set the scene first with climate change and the Paris goals. I'll tell you what these sensitive intervention points are and how we characterise them. And then I will go through a storyline that shows you how powerful these intervention points might be, how they're different to what policymakers might be told about, how difficult it will be to decarbonise, and then some of the opportunities and risks associated with that rapid decarbonisation. So you're probably aware, unless you've been hiding under a rock for the last 10 years, we've got a Paris Agreement that means that most of the countries around the world signed up for limiting global warming to well below 2 degrees above pre-industrial levels, preferably 1.5 degrees. which is an ambitious goal. It means we have to fairly radically decarbonise our system. If we keep going at the same rate, we'll probably blow that budget within less than 10 years. So a radical change to the system. A lot of people are concerned that this is not going to happen, and quite rightly, the young generations are up in arms about it because they're the ones that are going to have to cop a lot of the pain of that. And a lot of the new concern you probably heard about from Extinction Rebellion is around the idea of tipping points in the system, permafrost being one of them. That is a positive feedback in the system. Permafrost is organic matter that's frozen into the soil. There's quite a large area of it, mostly in the Northern Hemisphere, about the size of Canada and Russia combined. And if it starts melting, it releases that dead organic matter in terms of methane and CO2 into the atmosphere, which will create more warming, which will melt more permafrost, which will create more warming. And so you've got that feedback dynamic, which is concerning. The modelers I talk to at Oxford tell me that's incorporated in their models. But those kind of feedback dynamics also exist in our socioeconomic systems. And that's what this idea of sensitive intervention points is about. You might be aware of the butterfly effect. I hope you are, given the group that I'm here talking to. The idea that you can have a butterfly flapping its wings in one part of the world, influencing a tornado in the other part of the world. We got this published in Science, and the editor chose to put a picture of Greta Thunberg up there, which I thought for the article, and I thought that was a very good choice, because if you think about it, that photo was taken about 8 months after she first started protesting out the front of Sweden by herself, out the front of Swedish Parliament. And then through the amplification of social media, she spawned a social movement, the Fridays for Futures and the Sunrise Movement here in the US, which apparently had quite an influence on the 2020 election. They got Biden in, got rid of well, not for good, maybe, a denier, a climate denier in Trump, and brought in Biden, who has recently invested, started the put into policy the Inflation Reduction Act, which is, if it goes through, will be one of the single largest investments in clean energy technology. So that's the example of one small change that has an outsized impact on the planet. There are others out there that are looking at this problem. So I just want to point out we're not alone in our idea that there's feedback dynamics. If you look at it from a systems dynamics point of view, for instance, if there's more disasters, more climate change impacts, then more people become aware. And so there's a way that the human system can react to those disasters and give a negative feedback and hopefully decrease the amount of warming. But what we were looking for with the sensitive intervention points is actually those positive feedback points that could get you beyond the tipping point. This is one example. You've probably seen ads where they point out that Norway's got more EVs than anywhere in the world. It's actually quite a curious story. But basically, the government put in place a progressive tax system that meant that EVs were always slightly cheaper than their equal petrol alternative. And look at the difference between all the other countries, right up to the point of where their cost price parity, and then Norway, this massive change to the system just by getting it over that tipping point. So what makes points in a system sensitive? So that's an example of a critical tipping point or a threshold that you have to get the system component over. There's also critical points in the system. Say, for instance, if you put a carbon tax just on the power system, that would actually move most of the decarbonisation of the whole system, but you won't have to tax the whole economy. You just tax the power system, particularly if it goes through their supply chain. So that's a critical node in the system. And then there's critical points in time. The UK has got a Climate Change Act that happened in 2008. That happened because there was bipartisan agreement at the time. The Stern Review just came out. Business wanted clarity, and so one of these NGOs jumped on that idea, and we've got the Climate Change Act in UK, and their emissions have gone down ever since quite dramatically. So that's a shift in the system, and that's the idea, is that there's two different types. You can kick the system, like in Norway, you're kicking a certain technology and getting it over that hump, and so once it's cheaper than all the rest, then there's this dynamic that happens that keeps it out in front of the competition, or you make a shift to the system like a piece of legislation. That's harder to do, but it's also more powerful. And if anyone's familiar with Danilo Meadows' work, the leverage points that she has and the hierarchy of those leverage points is very relevant here. And what we were looking at was, well, how can we characterize these sensitive intervention points in order to rank them and prioritize them? So we're looking for criticality, how close the system is to tipping, barriers, what are the incumbents that are able to prevent that tipping point from happening. The fossil fuel industry is very powerful and has been doing a lot for decades now to try and prevent action on climate change. Hysteresis, if you get a political system that switches back and forth, and that decision is dependent on that, what party is in power, then you're not going to get the kind of lock-in that you need. Also, what's the size of the impact relative to how much investment or effort you have to put in? What's the scale of the impact? Is it global? Is it across all the sectors? What's the speed? We have to decarbonize rapidly, so that's important. And then also the risk potential. So what's the uncertainty around whether this will have the kind of impact we're looking for? What are some of the unintended consequences? And are there any trade-offs associated with it? So that's possibly a little bit boring, but that kind of sets you up in terms of the methodology that we apply to look for these components of the system. And we came up with a number of different interventions that we felt, based on the rankings, which were subjective, that had the potential for having outsized impact and with fewer barriers, fewer unintended consequences, fewer risks. The top one was investment in clean energy, renewables, technologies with consistent cost declines, and that's the one I'm going to be talking about a bit more. But there's others like enhancing climate-related financial risk disclosure. That's a big thing in Europe at the moment, the Task Force for Climate Risk Disclosure, where all the companies have to disclose their exposure to climate risk as a material risk to the company. That's not having the same sort of impact in America, even though the SEC is trying to push for that. It's become very political, but still it has a lot of potential in terms of promoting action on climate change. And actually a good portion of these kicks and shifts to the system have one feedback dynamic in common, and that is the clean energy learning by doing feedback dynamic. And that is that for certain technologies, the more you invest and deploy these technologies, the cheaper they get. The cheaper they get, the more people demand them, and then the more you deploy them. And so that positive feedback dynamic is one that I have identified as being particularly important, and that's what we spent a fair amount of time modeling and trying to understand that dynamic. I'll just set the scene a bit in terms of how what we do contrasts with what decision makers actually told about climate change. This might be familiar to you, this graphic. The black line is basically our global emissions climbing up through time to around 40 gigatons of CO2 at the moment per year. If we continue on that track, we get up into those 4 degrees hell on earth kind of catastrophic states. But if we manage to turn the ship around and decarbonize rapidly, we can get to those below 2 degrees level. That's a good portrayal of the uncertainty around the socio-economics and the dynamics of the system. But what decision makers are being told about how difficult it is to get to that 2 degrees is problematic from our perspective. in these models, basically, they apply a carbon tax to the system. And generally, if you apply any tax to the system, it slows down the economy. So in all these models, the economy suffers, the GDP suffers. It also impacts on energy use, because the less energy you use, the less emissions you have. And then even when we pull on those two levers, these models suggest that we need to build at least 13 gigatons of carbon capture and storage. Unless you're familiar with that, that's a large piece of kit that you add onto your power plant that takes the CO2 out of the flue gas, purifies it and sticks it underground. There's a plant in Canada that does 1 megaton a day. That's one of the largest that's in existence at the moment. We would have to build one of those every 3 days for the next 80 years just to get to 13 gigatons. And that's the optimistic scenario. We'd have to do more than one a day in the more pessimistic scenarios. So what's wrong with that? Well, sorry, there's one more point, is that because this is a piece of kit that you add to your energy system, it's more expensive. So energy prices go up as well. So it doesn't look like a nice story for policymakers, and you can imagine why they're being daunted by acting on this. So what's wrong with this story? One of the key problems is that the models have been systematically biased against some key clean energy technologies. This graphic here shows the actual PV costs coming down the black line through time, and then the projections from those integrated assessment models that the IPCC uses. And you can see that the majority of them are on the right-hand side. They're systematically biased. There's not too many that are overly optimistic. And there's some of them that look absolutely crazy. So, there's also the problem that they're not really based on the latest empirical evidence. They get out of date quite quickly. And it's vitally important because of that feedback dynamic. And you can see that this is on a logarithmic scale, and that gives you evidence that you've got a feedback dynamic because it's linear on a logarithmic scale. Whereas a lot of their modeled projections are not doing that. So to what degree are they incorporating these feedback dynamics in the models? Well, it turns out they do actually use those feedback dynamics in a good number of models, but they contain them because they're problematic, particularly because they've got this economic system that uses general equilibrium models that you have to put in decreasing returns to scale, which means increasing returns to scale is the less input the less input you get more output for less input. That's economies of scale. They put decreasing economies of scale in it to manage the mathematics of the problem to get unique equilibrium results, which seems kind of crazy given that there is a lot of economies of scale out there. You'd basically rule out the Industrial Revolution if you got rid of economies of scale. Also, the ones that do include endogenous learning also incorporate floor costs. So they say an expert will tell them that the cost of PV won't go below this floor cost. And you can see them in the green lines there with the actual PV costs coming down through time. You can see that those actual costs have broken through those floor costs over and over again. And so the experts come back and said, oh no, we've got a new evaluation. It's this cost. And then it breaks through it again, which is problematic because there's no real evidence for floor costs in the empirical data. But they're doing it in order to manage the feedback dynamic in the system. Also, these are really big models. They get out of date really quickly, and it's a very lengthy review process. But when you've got things happening so rapidly, and that is the latest PV prices, there was a bit of stalling with COVID, but now it's back on track. None of those models got down to that low level of cost for PV. So all of them are already out of date, and they were only a couple of years ago that they were put out. There's also another component of learning by doing, and that is complementary technologies. And that's the idea that with renewables, you want more batteries in your energy system. And if you incorporate EVs into that system, you can get clean energy powering your EVs. You're investing more in EVs, you're investing more in batteries, which means putting batteries on your grid is cheaper, which makes it cheaper to bring on more renewables into the system, which makes it cleaner and cheaper for you to have an EV. So I've asked the modelers from the International Energy Agency whether they include this dynamic, and they don't. And that was one of the dynamics that were important in our modelling. So is there a better perspective? And this is based on the work that Doan Farmer's done over the last decade on technological learning. But this is a different perspective that you can get from our modelling that I hope the policymakers are listening to. And I have presented this at COP, so some have seen it. That if technological trends continue for another decade, we'll be on track to meet the Paris target of 1.5 degrees. And meeting the Paris target could cost less than business as usual. You probably haven't heard that. You probably haven't heard that we could save money by solving climate change. And that's even without accounting for climate damages. So forget about all the impacts that we're having with tornadoes and wildfires and drought and so forth. Okay, so here's the evidence, and this is probably the main kind of graphic that you need to understand, and took a lot of effort to get the data for this. But what you see there in the brown, black and grey are fossil fuels moving through time, inflation adjusted, their costs on the left-hand side. And you can see they don't move more than an order of magnitude. They say over 150 years, the cost of these commodities hasn't changed much. Look in contrast to solar in the gold there, literally coming down out of the sky. But then you've got some other technologies there that are important. You've got wind in blue, you've got electrolyzers in green, and batteries in there in purple. The lighter purple, the pinkish one, that's nuclear. And interestingly, that's actually gone up in costs, a lot to do with safety and so forth. But we do contrast with nuclear in this model, and it's not a good story for nuclear. Now, on the right-hand side is deployment, and that's also on a logarithmic scale. And look at that, the growth of these technologies has been exponential. So what happens if that continues just for another decade? Those trends continue, and they've been going for the last 2 decades, so it's a fairly good assumption that they might continue. Well, we first have to understand, how we can, technological progress, that seems like a very difficult thing to understand or anticipate. Like, I was part of the internet revolution, and if I had bought Massachusetts.com, I would have got hundreds of thousands of dollars, but I didn't see how valuable that domain name would become. So it's hard to believe that we're going to be able to anticipate what these technologies are going to do through time. But it turns out once a technology becomes established, its trends are actually quite consistent. And there's 2 key trends. One is that not all technologies are the same. This is the price of US manufactured goods from 58 to 2011. You can see most of the technologies are around 0. So most technologies don't actually change their costs through time. But there's some outliers. There are, and some familiar ones, computing, that do consistently come down in costs through time. So not all technologies are the same. And those trends are actually really quite consistent. You're at college, you're probably well aware that college tuition and textbooks have been going up quite steadily through time, medical expenses as well. But technologies down there, you can see some have remained consistently not progressing, but others have progressed steadily for decades. And what I want you to note is how consistent that trend is. Year after year after year, those technologies continue to come down, adjusted for quality and all sorts of measures. So are there empirical laws here? In fact, there's 2 that are commonly used. Moore's law, you're probably familiar with, to do with transistors. The fact that you're going to double the number of transistors every 8 months, I think it is, through time. And that law works rather well on a range of different technologies. And you can see there on the x-axis you have time. So that is basically saying that technological progress happens through time. It's exogenous to the system to some degree. Whereas Wright's law is actually an older law that was developed by Paul Theodore Wright, who was a pilot in World War II, and he helped build planes for the war effort, and found that with every doubling of deployment of a technology, you got a certain percentage decline in the cost of that aeroplane in his case, but any product, it turns out. And you can see there that for that range of technologies, transistors, photovoltaics, hard disk drives, ethanol, both of these laws work fairly well. Interestingly, if you have exponential growth, which we seem we do, Moore's law is pretty much the same as Wright's law. So there's this exonerable, oh, I don't think that's the right word, but there's this juggernaut of technological progress that we can't seem to stop potentially with Moore's law, because I don't think any of the developers that worked on those CPUs knew that they were going to, or had that as their requirement, that they doubled the number of transistors. But Wright's law is actually really interesting because of the fact that it has a policy implication. The more you invest in a product that has these learning rates, the more you're going to be able to drive the cost down. And that, I would argue, is one of the powers of the Inflation Reduction Act, and what China has done, as you'll see, investing in this technology. What Doan and his group did is reformulated Wright's law to make it predictable. So putting standard errors associated with the predictions of where these costs are going to go based on deployment. They validated on over 50 technologies. And as you can see, since they put out that paper in 2016, the actuals have strayed actually further down to almost 2 standard deviations away from the mean, the long-term mean, but then it comes back to that long-term mean. And it's that long-term mean that's important. So what are the opportunities and risks of rapidly decarbonising? So what can we do with this understanding of technological progress that can give us some insights into how to decarbonise our global energy system? To do that, we built a model. It's comparatively simple compared to the integrated assessment models, but includes something like 90% of the world's energy system. And to break it down into as easy as possible to understand breakdown of what we're trying to model, we are taking a system that has dispatchable baseload energy and converting it to one that has renewables plus batteries. All the liquid fuels we're replacing with renewables plus hydrogen. So the entire fossil fuel system we're replacing with renewables plus batteries plus hydrogen, and you need electrolyzers for that. So 4 key technologies there: solar, wind, batteries, and electrolyzers. And we applied this Wright's law to each of those technologies. So for the fossil fuels, as I said, it didn't actually change much through time, so we put a random walk to them, an autoregressive function. But for those 4 key technologies, we use that prediction and develop the distribution of their costs based on the deployment in particular scenarios. And the red lines there show what the integrated assessment models have, as opposed to the predictions based on this understanding of the empirical evidence for these technologies. And when you combine them all in an energy system, lo and behold, it turns out that the median of going to a fast transition, which is purely based on renewables and batteries and electrolyzers to create hydrogen, it's $12 trillion. That's the median. As you can see, we get distributions there because we're using distributions in our predictions. And the median is actually, we're being conservative there because the median, as you can see, is quite a lot larger than that 12 trillion. But $12 trillion we could save with this energy system if we push a fast transition. And don't forget, that fast transition is us just continuing with the current trends. And given the fact that solar is now one of the cheapest forms of electricity on Earth, in most places on Earth, there's a lot of economic momentum behind it. So it's not a bad not an unlikely scenario, though those trends are going to continue, which is good news for everyone. And in terms of the emissions, that green line is that fast transition. That's our emissions coming down through time. That's just for the energy system. But if you see that green bar, that's the cumulative there, in juxtaposition to the light blue bar, that's the 1.5 degrees uncertainty range. You can see we're within that. The white section above that green bar is the other parts of the economic system that we didn't model. So land use change, some of the industrial processes. So if we can manage those other parts of the system, we can get to 1.5 degrees. So as opposed to what I said, the decision makers are being told about how to get to less than 2 degrees, that economic growth will suffer, you need to reduce your energy use, you need to build all this carbon capture and storage, and that means the electricity prices are going to be higher. Our storyline is that even just with this modelling, we didn't require any reduction in economic growth. We had the same economic growth for all those scenarios. We didn't require any reduction in energy use. Energy use management is actually a good idea. It's a really cheap alternative, so we should do it, but we don't have to get this result. And we don't incorporate any carbon capture and storage. But as I said, we don't get to zero for the whole economy. So there could be hard to abate sectors like cement or airlines that you might need carbon capture for. So we're not saying you don't necessarily need it. But because we reconfigure the entire energy system using this much cheaper alternative, electricity prices we estimate are going to be at least half of business as usual. And you can imagine, what that's going to do to the economy. Like, the Industrial Revolution was part of a big part of that was because of the availability of cheap energy. So energy is going to get even cheaper. So there's enormous growth opportunities coming with this revolution. Now, getting to more complexity components of the research that I was involved in, we took that trend, that model, and said, well, what does that mean? What countries are best placed to kind of take advantage of what's happening here? You're possibly familiar with the work of Hidalgo and Haussmann at Harvard and Notre Dame. They basically looked at, very clever stuff, they looked at their export data and said, what countries are exporting what products? Are they exporting two products that are similar to each other? And so what's the likelihood that another country that is making one of those products, like glass manufacturing, what's the likelihood that they could then move into making solar panels? And it turns out that's a good indicator of their potential in the future as well. Some colleagues at Oxford, Penny Mealy and Alex Tellenbaum, applied that to green products, and that's the data there for the green complexity index they came up with. There's my home country, Australia, in the dark green, looking like laggards, whereas the US has been at the top for quite some time. But look at China and its growth, and a lot of that has to do with their renewable energy exports. And but actually, a lot of that is to do with their deployment in their own country. They've deployed more than pretty much the rest of the world combined. And they're doing the same with EVs as well, which is a very smart move, because if this actually happens, that industry is going to grow tenfold. So China is really in the box seat, and the IRA is pretty much just trying to get America to catch up. And other countries like India are trying to do the same. But there are also, as I said, risks involved with these sensitive intervention points. You're kind of playing with chaos here. So you've got to be aware that you're bringing about runaway change. It's runaway change for good, but there could be some consequences to rapidly decarbonising the energy system. One of which happened in England over 100 years ago. In the north of England, when the coal mining industry, they were basically supplying the world with coal, that declined quite rapidly and wasn't managed particularly well. And you can see the difference 100 years later with those areas, and the deprivation in those areas 100 years later where they were doing a lot of that coal mining, where a lot of those jobs were. So not a very well managed transition away from coal there, as you can see. So we did some more modeling to look at, well, what might happen in the US. And this here is actually a representation of an NREL scenario that is very similar to what Biden's plan is, which is 100% renewables by 2035. This is actually 95%. And we're looking at the impacts on the labour market. We have a network of industries and occupations, so we match industries to occupations and skills. Interestingly, you can see the picture from the point of view of occupations is not so bad, because there's a lot of management and admin that's in the fossil fuel industry, as well as the renewables industry, so people can move between those different industries. So the picture's not so bad, but the reason why we looked at this more ambitious scenario is because it has that scale down phenomenon. So you're building out the new energy system, and then you're going to have to scale down. So there's jobs that may not last for very long. And in the literature, there's this green versus brown jobs dichotomy, which I don't think is particularly helpful, and it doesn't play out in the data. And what we did here, a student of mine, some particularly clever stuff using networks of occupational mobility networks. So that is how likely it is for someone that is working as a chef to then move into being a waiter, and likewise a waiter becoming a chef or going somewhere else. So what are the probabilities associated with those movements? And then if you have a decline in one of those related occupations, how's that going to impact if there's an increase in the other one or a decrease in the other one, if there's less people coming in or less opportunity for them to leave? So there's supply bottlenecks as well as demand bottlenecks in the system. So we looked at both of those. And I know this is not easy to look at, but basically you can see in the top right quadrant, on the right-hand side, you've got your in neighbours, so people coming from another job into your job. You can see wind turbine technicians out there. And on the top right, down the bottom, the bottom right, you see that huge growth in wind turbine technicians. And we're looking at the growth phase here, this section here with this graphic. And so that's where employers are going to struggle to find workers in this section here. Construction labourers to do that build up. And then workers are finding it hard to get jobs in their network, because you've got your out neighbours, the other jobs, what's happening to the other jobs that you usually move towards. And so you can see the contrast also in how they're being impacted by this transition. Power plant operators is a consistent decline, and some, like construction labourers, see that is a temporary growth scenario for them. We found that more jobs in the renewable-based energy system, but because it's going to be a cheaper system, it's very likely, or it's possible, that those jobs may not be paid as much as the coal industry. It kind of makes sense, otherwise it wouldn't be cheaper. Or there's less jobs, there's more automation possibly. Who knows? That's the other mega trend to worry about, of course. That dichotomy, as I said, is misleading. And there'll be significant regional skill shortages in stranded locations in both the scale up and scale down. And this is looking at the scale down here, where you've got this section of the transition, and you get power plant operators struggling to find jobs, as well as excavation machine operators and so forth. So wind turbine technicians looks like a good job to be in for the next 30 years. Finally, a piece of research looking at that fast transition and to what extent that's been incorporated into decision-making by central banks. Central banks stress tests since the global financial crisis, the system to major sources of stress. If you have one of the large industries like fossil fuels suddenly declining rapidly, how is that going to impact on the financial system? Unfortunately, what we found is that they're only stress testing with particular types of scenarios that don't have the full range of uncertainty associated with them. We contrasted it to that fast transition scenario, which has more positive impact in terms of the valuation, but it's also got a wider spread. There's some of the fossil fuel power operators are harder hit because the decline is so rapid, and that has to do with stranded assets. It's a simplistic model in some ways, but what we were trying to show is that the stress testing that's been done is not incorporating the full expanse of the uncertainty. So the conclusions. This is something that Jim Ski, who saw our work, is now working at the COP and the IPCC, said, which I thought was so good, that there's an opportunity to change the mood music that's being played to decision makers, because this is actually quite an optimistic story that we've told, and hopefully you think so as well. That strategic policy to trigger these sensitive intervention points can have outsized impact and promote rapid decarbonisation. For instance, a continued strong investment in key renewable and storage technologies could, over the next decade, put us on track to meet the Paris goals, cost trillions less than business as usual, need not reduce economic prosperity, but actually there's huge growth potential, particularly in the manufacturing of clean energy and storage products. And it could make electricity much cheaper for everyone, which for me kind of solves half the sustainable development goals, but that's a bit naive perhaps. However, it's not guaranteed. Those deployment rates are going to have to continue their exponential growth. They'll face considerable challenges, incumbent fight back, and risks, those labour bottlenecks. I was working in the South Australian government, and I was talking to them about the potential for the growth in some of these jobs, and their models are linear. And if you take 3 years to train someone in a particular job, you know, a non-linear dynamic is going to get ahead of you very quickly if your model is only training people for a linear change to the system. Stranded assets, as that last piece worked out, and the potential for financial disruption associated with, which all must be managed. If you're interested in any of this research, you can find that on my website, matthewcives.com. Thank you for your attention. Any questions?
Thank you, Matthew. Any questions?
So related to CO2 emissions, what's the role of developing countries in those projections? Do you assume them to be compliant?
So it is a global model, and we don't explicitly model particular regions. Developing countries have difficulties that the developed countries don't have in terms of getting the cost of renewables as cheap, particularly to do with finance costs. So there are more barriers within some developing countries, but not all of them. I'm talking Africa there, like India, for instance. We've modeled the transition in India. They've got the world's most ambitious hydrogen program, which within, I think, 8 years will take about UK's electricity system and apply it to producing hydrogen. And there's huge opportunity there for India. The growth of their production of electrolyzers, they'll be able to produce green shipping fuel, they'll be able to decarbonize their steel, and their energy system is going to be cheaper. So those countries that have the will, there's huge opportunities there. I think, to me personally, the onus is on the developed countries to show the way. They've got the technology and the capabilities, and there's some significant roadblocks, particularly that a high renewable based system is going to look probably more like the internet in terms of how it's managed and run. You're going to have virtual power stations and virtual storage all over the place, and you're not going to know where your power comes from. but it's going to be managed with an intelligent grid. I can see that rolling out in developed countries before developing countries, but that may not be the case. I mean, I was in China and I was buying everything with my phone. Like, I didn't need cash, and that was well before we were doing it. Parts of China are developing, but parts of it are very developed. So there's also the opportunity of developing countries to leapfrog with some of these technologies. America is weighed down by its past. It's bought into fossil fuels in a big way. You've got quite a history with it, and a lot of your emissions reductions are from your gas, moving to gas, which is great that you're reducing your emissions, but you're still locked into a fossil fuel system. So the faster you can move away from that, the better. And there are parts of America you could call developing. So yeah, plenty of concerns the world over.
Can I ask a follow-up? You might have better statistics on this. How much will the projected development in AI make the pie bigger in terms of the demand for energy? And that the statistics might make a difference in terms of, is there a chance, a short window of a chance for legislature to jump on that potential wave so that you don't have to necessarily shift?
Reducing its impact.
Well, it's more about if there is a higher demand for energy, then what you're going to build onward from this point could be moved towards the investments that you require, which would create the feedback that you talked about.
Yeah, I had a colleague look into the growth of data centers around the world, and the trend was quite scary. The growth was really dramatic, and he was coming up with projections that very few of us believed could be possible, but they are. Like, the growth of the demand for energy by servers and Bitcoin and AI, the growth is quite spectacular. And it has continued quite consistently, and as I've shown, technological progress, once it starts, can be quite consistent. I know another colleague, Penny Mealy, would say to me, that's not a problem. We don't actually have to reduce demand for energy as long as the investment is going renewables and electrolyzers and these energy system, energy technologies that have declining costs. You're driving the cost down. So it depends on how you're powering those systems would be a big part of it. I saw recently that the costs of solar panels have gone up in the US, in part because, is it Microsoft ordered some 12 megabytes or something of solar panels just recently. So the IT companies that are powering this revolution appear to be behind the renewable storyline. Google's doing something similar. Microsoft, I think, said they were actually going to not only decarbonize that whole system, but capture the past emissions as well. So wipe out all their history of emissions, which is great. So I'm not sure how they're going to do negative emissions technologies. They could do it with direct air capture, but hopefully they're going to use renewables to power that direct air capture. I'm not overly concerned with that. I'd be more concerned with the impact on jobs of that trend, because, for instance, in China, they've got 2 million jobs currently in the coal industry, and with our fast transition, that will decline within 20 years to close to nothing. But they've already lost 5 million jobs because whole villages of coal miners have been replaced with one kid and a joystick and a large excavator. So automation, even in the People's Republic of China, is having a dramatic impact on jobs. So that would be my bigger concern there.
I had a question on your fast versus slow scenarios. So what is the control knob for determining the scenario? Is it upfront investment? And if it is, do you factor in like borrowing costs in your analysis?
So we tested our conclusions against a number of different discount rates, which is similar to the idea of borrowing costs. There's a bit more complexity to actually modeling borrowing costs in the system. And it was consistent regardless up to about 10%. And getting anything beyond that is unreasonable in my mind. I'm not too concerned about that. I think there's a timing issue, but there's a huge availability of credit at the moment, so I don't think that's a problem at the moment. But that brings up an interesting point that you've seen in the record of wind, for instance, that for a period of time it stagnated and then progressed. Solar the same in 2000s, stagnated and progressed. They're all to do with supply chain issues. And one of Danilo Meadows' points around systems dynamics is if the system is moving too rapidly for the delays that exist in the system, then you'll get those oscillations. So there's an argument that a fast transition might generate more of those oscillations. And I would hazard a guess there'd be one in business cycles and borrowing costs as well that need to be taken into account, which weren't in our model. Yeah.
Last one. One last one, sorry. For me anyway. And since I see we still have a couple minutes, why is it that, so it's sort of a pessimistic question, but why is it that in these newer technologies for energy production, we have this exponential drop in prices, whereas with the mature technologies like oil and gas, we're not seeing that? Why is it, should we not expect new technology to reduce those prices? And if so, obviously that would change your forecast. But obviously the data you presented suggests that they're pretty flat over time. Is it because of this maturity? And why doesn't technology apply in those sectors?
It does, but remember I pointed out there's two key observations about the empirical data for technologies. The first one is that not all technologies are the same. Commodities are those sit into that doesn't actually change much through time. And there's an explanation for that in that when we start running out of a particular commodity, we put effort into finding more, we improve our technology to the point it seems that we get our costs to stay about the same. And then we have to explore some more, we have to come up with better methodology for doing that. And we keep it. So there seems to be this consistency through time with those sort of costs. Whereas things like solar panels in particular, the progress is in the manufacturing. So they've improved the manufacturing of solar panels now, and the deployment of them is easy. You stick them on your roof or wherever and plug them in and they work. They're quite amazing how simple they are to deploy. But the manufacturing process is really quite impressive. The thin solars using the sort of technology Kodak did for photographing, that's really fascinating stuff. And the silicon solar panels, what China's doing at the moment, they've got to the point where they have the process down so refined and so well understood. They've built a recent factory that supplied about 20% of the world's solar panels, just one factory. It was modular. If they needed to build another one, they just build it right next to it. And they've got another 20%. So you can see them taking those economy scales. And so there's a certain magic to technologies. Which are the technologies that are actually the ones that have these learning rates? The three rules that I came up with, and I'm just coming up with them, is mass appeal, mass manufacturing. What's the term I'm trying to come up with? Modulation, mass manufacturing, and mass appeal. So carbon capture and storage is a big piece of engineering kit. Like they're massive, and it's a lot of chemicals and so forth to try and capture that. And they don't really have mass appeal. Like the idea that you're putting this big flue gas capturing device on your power system, your electricity is going to cost more. And modularity, that's not. It's a large piece of kit. The same applies to nuclear. They're talking about small nuclear reactors, but the economies of scale in nuclear reactors is actually in large reactors, mostly to do with the cooling system. So they've got to overcome those natural economies of scale to get small modular reactors, and I'd be surprised if that gets pulled off. They've got to do things like harmonization, which solar panels already have, which is the idea that you can plug and play different components together to make almost like a kit. I can't see that happening for nuclear plants, maybe for one manufacturer, but not all the manufacturers. So yeah, there's a certain magic to certain technologies that seem to work a lot better. And batteries, electrolyzers, solar and wind all fit those criteria.
Any more questions? Let's thank Matt again, and thank you all for coming as well.
Thank you.